Okay, so we talked about, oh, sorry about that, directing effects. And so what I want to do is just do a few examples of dealing with that topic, just to make sure we have it. And so let's go back up to here. I'm just gonna cut this out. All right, let's look at that first example. Excuse me. I'll just redraw it down here. All right, so we're going to take that product and I want to brominate it. All right. So we're going to predict the outcome of that reaction. If I brominate that product, first question is this a donor or an acceptor?
Donor.
What will make it a donor? Right. Remember, a donor, we're talking about electron donor, either through induction or through resonance. Does this group have electrons that can donate into the ring? Now there are 2 lone pairs on oxygen, but they're not gonna be donated into the ring. Right. The fact that you have a carbonyl, which is polarized in this direction, making this partially negative and making the carbon partially positive. Right. If that carbon is partially positive, it's not a donor, right? It's an acceptor. Acceptors accept electrons. And in order to accept electrons, you have to have either a full positive or partial positive, and be in order to be able to accept a pair of electrons, or even to accept electrons inductively. So that carbonyl makes this group, just the whole group, just because it's attached, that ring is attached to the carbonyl, doesn't matter. That carbonyl makes this an acceptor. Right? A donor has to be able to push electrons into the ring. So if I brominate that, where would my bromine end up? Remember, if the ring is already substituted, I have a ring like this and it's got a substituent on it already. I got three positions that are going to be available: the ortho, meta, and the para. Right, this is 1, 2, and then 1, 3, and 1, 4. But depending on the nature of the substituent on the ring, right, that's going to determine whether or not it adds in an ortho fashion, a para fashion, or meta fashion. So if there's an acceptor, what position does the acceptor activate?
Doesn't the acceptor, aren't those at the meta phase, the activated phase?
Yeah. So if and I forgot, let me put some bonds in here. If there's an acceptor on the ring already, it's going to activate the meta position, right? So that's going to be this position right here. So this is 1, that's 2, and that's 3. So the 3 position. So if I would have brominate this, the bromine is going to end up here. And that's strictly because of the presence of this group, and in particular, the carbonyl attached to the ring as a electron pair acceptor. Right, so acceptors are meta directors. All right. Let's take the next product, which was the bromine, or the brominated ring, sorry. And I'm going to isolate this. Right, so remember, I think I gave you a kind of a little, not an exhaustive list, but a list of what could be a donor, what could be an acceptor, what class would halogens fall into. There's a halogen already on the ring. Is that going to act?
Donor.
It's a donor. Good. So if it's a donor, what does that mean for the positions that get activated?
The
It would be
position.
ortho or para.
Okay, so the ortho position and the para position, right? If we were numbering, which we don't, but dye-substituted rings, but if we were, this would be 1, 2, and 1, 4, right? So if you count to 4 away from the position where that first substituent is, right? You can see where the para position is. It's basically 180 degrees to the substituent, and then the ortho position is at position 2. All right. So when I isolate this, what am I adding to the ring? We're doing a Friedel-Crafts isolation. What am I adding to the ring?
It's the whole thing. I'm sorry, you can go.
The whole thing?
Except CL.
So I'm adding this group right here. Is that right?
Yes.
And because I have a, a directing group on the ring, a substituent, I'm going to add that at both the ortho and the para site. All right, so I'm going here. I'm going to add a group here. And then I'm also going to get another product here. Right? This is my ortho product. This is my para product. And you do get both, but there is a little bit of competition based on the sterics of the reaction. So the ortho product is a little bit less favored because of the proximity of those groups. So normally your para product would be major. So the para product is normally your major product, right, due to sterics. Because of the, the closeness of the groups in the ortho product, that kind of destabilizes that a little bit. All right. Questions? Any questions about that? About anything?
Yes, I have a question. I'm still
Go ahead.
confused as to where do we start counting when we're determining like the ortho, para, metaphase? Where do we start counting?
Here,
Okay.
the carbon where the substituent is. Because again, we're adding to a ring that's already substituted with one substituent.
Okay.
Right? So wherever that substituent is, that's position one. And everything else is relative to that.
Okay. Thank you.
Mm-hmm. All right, let's do the last one. And let's calculate it again. Right, so that tert butyl group is already on the ring. All right, what is the predicted products, or what are the predicted products for this reaction? So the question is, what type of group is the tert butyl that's already attached to the ring? Is it a donor? Is it an acceptor? Right. Remember, if it's a donor, it has to be able to take a pair of electrons from somewhere.
So it's an acceptor.
Hold on. Let me back up. If it's a donor, it has to be able to give a pair of electrons or give electron density. If it's an acceptor, it has to be able to take a pair of electrons. My bad. So let's go back up to here. Right, donors are heteroatoms with lone pairs, alkyl groups, halogens. Those are examples of donors. And then acceptors would be carbonyls, nitriles, nitro groups, trifluoromethyl, like which would be inductive, accepting. So when we go back to here, what type of group is on here? I heard you say that it was an acceptor, but that was based on me saying the wrong definition, I think.
So it is a donor.
It's a donor. All alkyl groups are donors. And if it's a donor, and again, it doesn't have to be donation through resonance. It can be donation through just induction, right? All of those carbon-carbon bonds make that alkyl group electron rich. So it's kind of inductively pushing the electrons into the ring, but not by resonance. All right, so if it's a donor, what type of, excuse me, what type of director is it going to be?
You mean like what type of products will we make?
Mm-hmm.
The ortho and para?
It's an ortho-para director, right? All donors are ortho-para directors. Right, so I'm going to get two products. Is that right? What would they look like? Somebody want to draw those in?
Would you include the BR in it?
Say that again.
Would you include the BR in the product?
No. Remember, your electrophile is going to get activated.
Okay.
Right. So that's going to actually become a carbocation that the ring attacks, if you recall from the mechanism. So the bromine is not involved in that, in the product, right? There's no bromine.
Okay.
Okay. Okay. Okay, great. Right, so the ortho product is basically 1,2 substituted, and then the para product is 1,4 substituted. All right. So if you have the basic concept that we're getting at is if the ring is substituted prior to the reaction that you're trying to do, whether it's acylation, alkylation, halogenation, nitration, sulfonation, it doesn't matter. If that ring is substituted, when you add in whatever electrophile you're adding to the ring, the substituent on the ring is going to dictate where your electrophile ends up. If it's a donor, it's going to end up at the ortho and para position. You're going to get both products. If it's an acceptor, it's going to end up at the meta position, right? And you only get one product there, right? Any questions? All right. So that actually is the end of the aromatic section. So what I want to do now is just introduce you to the next section, and then we'll actually stop for today. All right. So for the next section, we're going to be looking at characterization methods. So we're looking at these different characterization methods. We're going to start out looking at infrared. Right, and so with infrared spectroscopy, that particular method allows you to identify functional groups. Right, it allows you to identify functional groups, and then we're going to look at NMR, which is short for nuclear magnetic resonance. Right, and that identifies the carbon-hydrogen framework of a molecule. And if you took organic lab with me, part 1, then you've already been exposed to NMR, right? When we did aspirin, and at the end we did like this NMR assignment. Right, we did an NMR assignment, and you saw like what the spectra looked like, so on and so forth. So I'll show you what each one of these spectra looks like in 1 second. All right, and then let's look at the third method, which is mass spectrometry. Call it short MS. So mass spectrometry, that gives you an example. I'm not an example, an idea of size and molecular weight. Right, that's what it measures. It's a method that's used to confirm whether or not you have a particular product that you synthesize, and it tells you the molecular weight, and it breaks the molecule into fragments so you can look at the different fragmentation patterns and things like that. And then finally, we're not going to do a lecture on UV, but UV spectroscopy. right? That is that helps you to identify pi systems and conjugation. All right. So those are like really four major characterization methods. So infrared, NMR, mass spec, and UV. So let me switch my screens real quick because I want to show you. I want to show you what each type of spectrum looks like and what the instruments look like. And then when we get into talking about like the different methods, of course, we'll do more, but I just want to show you that. So give me 1 second. I'm gonna pull this up and find it. Oh, here we go, right here. Perfect. Yeah, so again, infrared deals with identifying functional groups. UV identifies conjugated pi systems, mass spec, size and molecular weight. And then NMR, you can identify, you can basically determine a structure from an NMR. If all you have is an NMR and the molecular formula, you can actually deduce a structure from it. And there are different types of NMR too. There's proton NMR, which is 1H, carbon-13 NMR, fluorine 19 NMR, deuterium NMR, silicon NMR. There's a bunch of different types of NMR. It just depends on what type of probe you have in your instrument. So this spectrum on the screen now is an example of a infrared spectrum. And this is vanilla and it's kind of fuzzy looking, but every one of these downward spikes on this spectrum has a meaning, right? So the spikes that you see right here, and it's hard, we'll talk more about the x-axis and the wave numbers and all that stuff when we get into this, but the spikes you see right here correspond to aromatic, the aromatic CH bonds, the stretching and bending of those bonds. The one you see here corresponds to that OH group. And then this big spike right here corresponds to your carbonyl. And then this spike here is going to correspond to your CO single bond stretch right here. So when you take an infrared, this is what you're going to see. You'll see absorbances at particular wave numbers that are indicative of specific types of functional groups, right? So every functional group has its own absorbance. Of course, some overlap because they're close, because they may be similar in type. Like for example, the carbonyl stretch that you see right here, it's probably about 1750 to 1800. That stretch can be ester, aldehyde, ketone, amide, can be a lot of dip, carboxylic acid. A lot of those stretches kind of show up in the same place. So you will have some overlap there. So this is not a method that's definitive as far as like determining a structure, because you could have a carbonyl stretch, but you might not know what type of carbonyl it is. All right. It can be any type of carbonyl, but it's going to show up in the same range. And the alcohol stretch as well. I mean, that's there. There's not many stretches that overlap or look like the alcohol stretch, but we're going to talk more about that later. All right, so this is an example of a mass spec. And on the y-axis, you have relative abundance. And then the x-axis, you have mass over charge, but the charge is normally +1 because what you're fragmenting is a radical cation. And so that mass is normally, the charge is normally +1. So what you have here, let me move this so I can see. This is for pentane. So pentane has a molecular weight of, let me see, 5, that's 60, 66, 6, 72. So pentane has a mass of 72 grams per mole. So that's going to show up right here, right on the mass spectrum at 72. And then all of these other pieces, the 57, 43, and 29, those are fragments of pentane. So in a mass spectrometer, you bombard this sample with an electron beam and start basically shattering it into different pieces. And those pieces get picked up by a detector. And then you see them on the x-axis, the masses of those, because every fragment is going to have a specific mass, right? Like for 29, that's this fragment right here. So the CH3, CH2, that little fragment is 29 grams per mole. So that's that piece broken off from the chain. So that's why you see at 29, right? And then at 43, it would be this fragment, right? CH3, CH2, CH2. So that's a 43 grams per mole. And then that fragment shows up there, right? And then these other smaller peaks are probably like that fragment losing a hydrogen, right? So 42, and then 41, and then 40, so on and so forth, right? And then 57 is another piece broken off, so that would be these 4 carbons, and then the CH3 group would be broken off here too. That's not showing up down here at 15, but that's what that would correspond to. So when you look at a mass spec, you have a molecule that you basically shatter into pieces, and then you get the masses of the pieces show up on the spectrum. And then for NMR, this is a sample NMR. You have multiple signals, and the signals are going to be based on the hydrogens. If it's a proton NMR, the hydrogens in that sample that are what we call non-equivalent, right? And they're going to be split into different types of patterns. Sometimes a signal may be split into 4 lines or 3 lines or 2 lines, and you can see that here, right? And every signal is going to have a specific location, right? So this molecule right here, you can see 1, 2, and then 1, 2, 3 aromatic signals, and then these other 2 signals right here, the triplet, and then the quartet, right? So every hydrogen that's different in this molecule is going to give its own signal. So you can see here, you got 3 different signals down here between 7 and 8. Those are aromatic signals. So those are going to correspond to hydrogens on the ring. And then the quartet is going to be this signal right here, these 2 hydrogens that are adjacent to a CH3. And then the triplet will be these 3 hydrogens adjacent to a CH2. So we're going to talk about how you determine the splitting pattern, how you determine the location, all of that stuff, right? So that's an example of an NMR. And then for UV, this is an example. And you can see you have a conjugated pi system here, and it has a maximum absorbance, lambda max, the maximum wavelength that it absorbs, and it's at 235 nanometers. So, but we're not going to talk much about UV. We're going to focus mainly on NMR and then infrared and mass spec. But yeah, so that's what's coming up in the next section. So we're actually going to stop here. I'm going to stop a few minutes early. So unless there are questions about anything that we've talked about, then we're going to